me share my screen. We can kind of dive into a new topic today. We're going to leave behind mat foundations. We will not, we kind of got into mat foundations for just one lecture. There's more to mat foundations than we talked about because mats are so large. You know, they have different shears throughout, and it gets kind of complicated, but we're not going to dive into that. And usually when you do design a mat foundation, that's a pretty big deal. You're typically not a mom and pop shop when you're designing a mat foundation, and you have access to some software that will help you calculate those intricate details of kind of the mat foundation. And it's really what the structural engineer would need to use, because he needs to decide where to put the rebar, where the mat is in tension, where it's in compression, where those peak shears and moments are, and that's how he decides how many layers of rebar and then where it goes. And to me, for a geotechnical engineer, that's never anything that I was really involved with. That's more of a structural engineering. Geotechnical engineering is understanding the soil conditions and recommending that, hey, this is actually a good site for a mat, and then let the structural engineer take it from there. Give him his, ultimate bearing capacities, and then they can get creative on the shapes and sizes and the depth of the concrete. So anyway, we're leaving mats, and now we're moving into lateral loads, lateral earth pressures. So let me share with you. Screen. So we got so many screens going on here. Hold on. All right, give this a try. Can you see that? Should pop up and say lateral earth pressure at rest. Okay. What is lateral earth pressure? I want to try some iClicker. Let me see. So, okay, so today, let's see. Can you see where it says outcomes? Let my screen stop. Can you hear that or see that?
Yeah, we can see you.
Yeah.
Okay, all of your Zoom pictures stopped responding, so I'm pushing Zoom to the limits. All of your video feeds froze, and so you're all paused, and you can see Renata scratching her head, but it is paused on that moment right there, and so I can't, you can see, then I'll just keep going on. So today we want to talk about how to figure out lateral earth pressure behind a wall at rest. We want to figure out and understand the Rankine active earth pressure behind the wall. Now, we covered lateral earth pressures in 341, and so this will kind of be a review. Hopefully some of it's familiar, and there's a really good review for lateral that I highly recommend for that was given by Dr. Frankie out of BYU. In Provo, when he taught the 341s class to his students. And so if you go back and watch that, I even grabbed a screenshot that I really liked from it today. But it's about 50 minutes and it is excellent. So watch that when you've got some time. And I posted this link also on the announcement page of Canvas. And so you can click right on that instead of trying to type it all in. So now, is this a big deal? Lateral earth pressures? Well, I've got a little video that I want to show you about how lateral earth pressures can kill. So your videos are all still not responding. So can you guys just say, can you see this KSL video thing that just came up?
Yeah, we see you.
Yeah.
Okay. All right. So let me just play this. Let me get my video, let's see. Oh, man. Might lose you guys. Things are not looking good. My Zoom's locking up. Can you still see everything?
Yeah, and we can hear you.
Dang. Okay. Well, my taskbar to control Zoom is totally locked up. So what I'm going to do, because if I play this video, there's no sound. And so I wanted to go to edit my sound settings, but Zoom is totally freaking out. So I'm going to log out and log back in really quick, just because you need to hear this video. It's only like 2 minutes long, but if you don't hear the sound, it will be pretty pointless. And I won't be able to annotate or anything. So Jacob's a co-host. Hopefully he'll keep the class going. I'm going to log out of Zoom, come back in, and then I'll share this video. So I'll be right back. Jacob, can you kind of...
Hey, do you want me to just play the video while you're logging back in? I have it pulled up and could share it and get it playing.
Oh yeah, play the video with sound. I'll log out, log back in while you all watch that video. Perfect.
Perfect. Sounds good. See you in a minute.
All right.
All right. Can y'all see that screen? I just assume yes.
I think I still see Brother Smith's frozen screen.
It is too.
Oh, awkward. So it should kick him off of screen sharing. Share. And then should be sharing this right now. Are you seeing this video, or is it still Brother Smith's frozen screen?
Still frozen screen.
Dang. This is awkward. Interesting. Okay, now he's gone. All right, now we'll try this one more time. All right, you see my screen?
Yeah, there we go.
Perfect. Let's get this playing.
Tough news, Felicia. Thank you for that. New today, a devastating situation at a home in Alpine. A construction worker killed while building a backyard swimming pool. Shara Park tracking that story and several others at this hour in the Breaking News Center. Shara?
Yeah, Dan, this is a really sad situation here. I just got a text from the Lone Peak Fire Chief. He tells me that the worker killed in this is 53-year-old Luis Moran. Now, here's what happened. Here's what we know about it. Rescue crews were called to the home near 700 North and High Ridge Circle Wednesday afternoon to find 53-year-old Moran, a contractor, buried up to his waist in a trench being dug for that backyard pool. Lone Peak Fire Chief Reed Thompson says the victim quickly succumbed to his injuries before they could rescue him, and he died at the scene. Chief Reed says that Moran was working in an unsecured open hole.
The victim was in a trench that did not have any security measures in place, i.e. shoring, and was deeper than the what OSHA requires at 4 feet. And so as a result of that, you've got heavy dirt and other material that can potentially fall or collapse into the open hole, which is what occurred.
Well, this became a very technical recovery effort. A special team with trench rescue certification was called in so that they could remove the contractor here without putting anyone else in danger. OSHA is now investigating this situation.
Is Brother Smith back yet? Looks like no.
If he was a private contractor, was he just working alone?
It's a good question. So looking through here, I'll share my screen again. Yeah, we can just look through the article here. Actually, just one second. Let me change my sharing settings real quick. All right. You're seeing the article right now?
Yeah.
Perfect. Let's see. Yeah,
It said there were other people on the site, so maybe they were other workers.
makes sense. Yeah, there was someone who recognized that he'd gotten into trouble and got help. Yeah, so I've not taken this class before, so I'm not sure exactly everything you've been learning, but what types of principles have you been studying that might relate to this new story, or why do you think Brother Smith may have shared this?
So I think one of the cool principles, and I'm not saying this is cool at all what happened to this guy, because that must have been awful, but he was only buried up to his waist, is what they said. And that killed him because it was so heavy. And I couldn't even imagine like being just buried up to my waist and that being so heavy that it would do that much damage to me. But
Yes, we're back.
Awesome.
Sorry about that. I had to do a complete restart. Control Alt Delete didn't even work. It straight up held my power button for 5 seconds. That was brutal. Okay, did you watch the video?
Yeah, so Brother Smith, to get you caught up, we watched the video. We had a comment from Josh about how just heavy that material was. That talked about the fellow who was killed was only buried up to his waist, and it was still fatal because of how heavy the material was. And that's where we've left off in the conversation.
Excellent. Yeah, I mean, that's sad. That's scary. The slope failed. I mean, there's multiple things going on in there. First, slope failure, which we talked about. Then second, the pressure. I mean, the guy was buried to his waist. It didn't even go up to his head. And so there was no like lateral, like vertical forces pushing down on him, but it was this side pressure, this squeezing, the same pressure that your ears feel when you're diving down 10 feet in the pool trying to grab that brick off the bottom. Your ears are just bursting. Well, soil does that same thing. That's what we're going to talk about today. So let me try to share my screen again. See what happens. I don't even know what's going to. Like everything's gonna, let's see, how do I share? I guess I don't have any more sound. So okay, so any thoughts on that? Has anyone else been in a trench collapse or seen something like that?
I haven't been in one, but when I was an inspector, that was one of the big things we always did was make sure trenches were safe.
Okay, tell me about this where you were inspecting. What was that?
So the first project, they were putting in a new sewer line. And so, you know, when you're laying pipe, people are in the trench all the time. And so they didn't want to have to deal with a trench box the whole time. So they subbed out the street down 2 feet because they were going to put in new sub base for the road. And then they only had to go down another 4 feet. But what they did is when they excavated, they V'd the slopes way back. So they were at 4 feet most of the time, which is OSHA approved, but then having them V it at the same time made it so we had a much less or lower chance of this happening.
Mm-hmm. Yeah, I mean, you will have knowledge that the common construction worker won't understand about soils. And if you're ever on a site, you have a responsibility to warn people of the safety hazards that they're unknowingly entering into. If you see folks jumping in and out of trenches, installing a utility line, and it has pretty steep slopes and it's pretty deep, you know, like Adam said, OSHA requires anything that's over 4 feet deep to have some type of slope back. You know, you cut the edges of the trench so it's sloped, or you have a box protecting you. So it's all for their safety, because at any time a slope failure could happen, sand could slough in, and it's not necessarily the sand landing on your head and knocking you out and suffocating you without air. It's those extreme horizontal forces. Does anyone know, just rule of thumb, approximately what the ratio between the vertical and horizontal forces are in a normal soil? So if you're down,
I watched the video that you sent out earlier, and it said that it was about half of the vertical pressure.
Yeah, so let's just do some math. Like, if this guy who was killed, you know, the trench buried him, you know, 3 to 4 feet of material was coming in on him. The forces that he'd feel on the side, let's say the unit weight of that material was 120 pounds per cubic foot, and then maybe there's 4 feet of it, you know, on him. He would feel, you know, 4 feet times 120 pounds per cubic foot of pressure pressing in on his side. And so, but not all of it. It would be about half, like you said, Josh. So whatever half, so it'd be about 240 pounds per square foot. So a square foot of your body would be like if someone stood on you that weighed 240 pounds, you know, with their feet. That's pretty much, that's what you're feeling. And that's just 4 feet of soil. that weighs 120. I mean, that's 240 pounds. That's a lot. And a person that was wearing some shoes, you know, that's almost a square foot. So those are the kind of pressures that you could be feeling. And that's over each square foot of your body. And so imagine having like 4 guys that each weigh 240 pounds stepping on a different part of your body. You know, these are the kinds of conditions roughly that the people that get stuck in these trench collapses are feeling. And it just goes up as the depth increases or as the unit weight of the soil increases, or if it's kind of saturated and wet. So anyway,
So
it's one. Go ahead.
if it only gets you to the waist, is a lot of the problem like blood flow being cut off? And
Yeah, I think that, like, if any of you have like grabbed your wrist and squoze it and watched your fingers turn blue and then open your hand and it's all white, I mean, that's what's going on. I think that usually people don't die immediately. It's like the longer you're in there, the worse it gets. And the specialty crews that come out, their number one goal is to try to relieve the pressure as quick as possible. Yeah, it's scary. But so lateral pressures, you've felt them before, but I wanted to do eye clicker today. So let me just try that. You have to just bear with me. This is my first time using technology. I want to get good at it. But you guys are my guinea pigs. So it's taking a little longer than I want it to take, but when I'm good, I'll be really good. Okay, so the next question is an iClicker question. So I want you guys to all log into iClicker and get ready. I've got 3 questions just to gauge your level of understanding before the class starts. So the first one, is lateral in water greater than the vertical pressure? So I'm talking about less than the vertical or equal to the vertical. So is that lateral, that horizontal pressure in water, is it going to be greater than, less than, or equal to the vertical pressure? So we're talking about water here, not talking about soil yet, just water. What's your understanding at that point? So it's open, take the poll. There should be about 15 responses. I've got 5 so far. I'll give you about 10 more seconds. In water, lateral pressure, is it greater than vertical, less than vertical, or equal to the vertical pressure? So I got about 12 responses. Let's stop the poll. 14, 15, nice. Snuck it in there in the last seconds. Okay, I'm going to stop it and I'm going to look at it. So we've got, interesting, quite a range. A lot of people said it's equal, but we had some people say it's less, and then some people say it's greater. So that's good. So now I know kind of where you're at. And so the correct answer is C. When you're in water, the pressure at all around you is equivalent in all directions. That's the unique thing about water. And what we just said about soil is, you know, the horizontal forces on soil are about 1/2 of what the vertical is. And so this is kind of a diagram to help you explain it. If you're in a swimming pool and you were this little particle right here, you can see my mouse, probably can. Oh man, okay. I want to draw this. Okay, so you're this little square particle right here, and I'm wondering, this vertical pressure, it's the vertical pressure that you feel is equivalent to the depth that you're in the water times the unit weight of water. So if you were 10 feet down, you would feel about 624 pounds of pressure, but the pressure that's acting vertically is equivalent to the horizontal. It's exactly the same. You can see these 2 equations are the same. That's because it's an isotropic material. So hydrostatic pressure, water pressure, is equivalent in all directions. But now check this with, if this is ground, if we just replace that swimming pool, filled it full of sand, the depth, vertical pressure that you would feel is same thing. It's equivalent to the depth times the unit weight of that soil. So in this case, it wouldn't be 62.4, it'd be 120 cubic or pounds per cubic feet. However, look at this. The horizontal forces that you're feeling is similar as the depth times the unit weight, but we add this modification factor. This is called the coefficient of at rest. And so this roughly, which we just said, is about 0.5. And so if you multiplied 0.5 by the depth and your unit weight, that would be the equivalent soil horizontal or pressures that you're feeling, this lateral earth pressure. All right, we're going to get into more of this little lot, but I just want to kind of get a feel for where you're at. So here's another question. So if you look at this wall right here, kind of look at it, you can see there's a surcharge, there's some water table, there's 2 layers of sand, one's loose, one's dense, 4 feet, it's 6 feet tall, frictionless wall. We haven't covered any of this, but based on your current understanding, let's open up the poll. Is this wall in an active or a passive condition? We haven't even talked about those yet. I just kind of want to see where you're at. Is it an active, passive, or neither? So respond. I'll give you about 20 more seconds. Think about this. We've not talked about it, so don't feel bad if you get it wrong. Just, I want to kind of, your gut hunch. Is this active, passive, neither? Because so far we've been talking about at rest. All right, 5 more seconds. Go ahead and put in your responses. All right, I'll stop the poll. Let's look at what we got right here. Okay, I'm seeing this majority, well, 60% said it was 9 of you said it was active, and then the other 6 of you said it was passive. Okay, so this is interesting. So we haven't talked about this yet, and I won't give you the answer right now, but we'll take this poll at the end of class and we'll see what you do, how you do based on what we learned. Okay, one more slide to gauge your understanding. Which has a greater value, Ka or Kp? We haven't talked about these yet either, but let's open up iClicker and go ahead. Which has a greater value typically, Ka or Kp? So Ka stands for the coefficient of active lateral earth pressures, and Kp stands for the passive lateral earth pressure coefficient. So which one is typically greater? So I'll give you another 10 seconds. A few more of you to respond. And the good news is when the class ends, you'll probably get 100% on both these polls. All right, 5 more seconds, 2 more responses. All right, I'm gonna stop the poll. Let's see what we got here. All right, 15 of you responded, interesting. Okay, so many of you, majority, but not by much, half said that Ka is greater, then 40% said Kp, and then 13% they're equal. Okay, so I'm just gonna say the majority of you got this wrong. So this is good, now I know where you're at. So let us begin. So the reason we're talking about lateral earth pressures, sometimes called LEP, is because this is going to be on that fundamental of engineering exam. This is going to be on your PE exam. I saw a question like this when I took my test to become a professional engineer. So let's talk about some of these different conditions. We're talking about, there's 3 states that a soil can be in. A lot of the equations that we've used so far have dealt with this at rest condition, kind of this middle condition. You're in the ground, the soil's not kind of sliding and moving to kind of free falling from a kind of like a slope failure. It's not moving in one direction. It's not being compressed and pushed into the, it's just sitting in the ground at rest. And so at rest is the condition that soil is, it's in equilibrium, there's no movement. This is a screenshot from that really good lateral earth pressure video that Josh watched before class that I'm encouraging all of you to watch. It'll explain this really good. So let's talk about lateral earth pressure. So you can imagine, how does an anchor on a boat work? If you have a boat and you throw an anchor over into the water, it's going to kind of go down, grip the soil, and then kind of hopefully dig into the soil and kind of just start dragging until it stops. But what is that force that stops it? What are you creating in there? You're creating a passive condition. That anchor, part of it is a wedge, and it's kind of, you can imagine if this is your anchor, it's pushing on these sort of soil particles, and it's pushing them on in a horizontal direction. and it's increasing that that force, that pressure, and we call this the passive condition. You can imagine it. You can also create a passive condition if you had a wall like this wall shown right here, and if I pushed into the wall with some force and tried to push that wall, I just tried to push it straight in. I didn't try to tilt it over. I just pushed it straight into that big soil mass behind here. The soil would resist that compression with a coefficient, and we call that when soil is being compressed, we call that a passive condition, and the wall was moving towards the soil. Now you can imagine, on the other hand, like that iClicker question that we just showed you, there was a picture of a wall. It had some layers of sand in it. There was a water table on it. There was even a big surcharge up here, and all those loads are kind of acting on the soil, and you can imagine it's kind of trying to bulge and push that wall over, and it almost is going to try to knock it over because all those forces are acting. I mean, soil doesn't want to stay square like this. If you've driven by a construction yard that has big aggregate stockpiles, the soil wants to sit at its angle of repose, which is very similar to its internal friction angle. So soil doesn't like to be in these square shapes. Mountains are not square shaped. Mountains typically are shaped like the pyramids, and that's the state the soil wants to get to. So if it's not in that shape, it's trying to get shape. And so you can imagine this wall right here, it wants to get into this. My mouse does funny things sometimes, but you've got soil that wants to get like this. However, it looks like this. And you can imagine this piece of soil wants to come down. And so it's going to be pushing on this wall. So that's an active condition. When soil is pushing on something, it's in extension. It's falling away. This wedge is falling away from that pyramid that it wants to stay at. And so the soil is actually a little bit, it's looser, it's falling, it's in tension. The soil is in extension. It's moving, the wall is moving away from the soil. So those are three states that soil can be in. It's either at rest, it's not moving anywhere. It can be, you could be pushing on the wall, or you can be an anchor. You can even think of like a basketball hoop. If you drilled a basketball stand, it also has both conditions on it, right? Or if you put a stand in the ground and then you're pulling on the top of that stand, you can imagine the bottom of the stand is trying to push out, and so it's kind of in a passive condition. So there's many instances you can probably imagine about these different states, this lateral earth pressure. So here's just another cleaner example to talk about these conditions. Here's an at-rest condition, and most things are not at rest if they have like a wall holding them up. If you see a retaining wall, a rock wall, a block wall, there's many types of walls. You've probably seen walls everywhere. And if they're holding soils back, that soil is trying, it's usually in an active state. It's trying to slip down this plane and budge that wall forward and push it out. So when you have that condition, it's active. This condition, this at-rest condition, is rare. Most soils are in an active state right here. The at-rest soil condition is typically when you have flat ground and there's no retaining wall. So if you see a retaining wall, you can just assume there's probably some active lateral earth pressures involved. If you had to assume, you would assume active. Now passive, that's rare. Normally walls on their own do not move into a soil, as shown in this example right here of the passive. This shows that there's some force on here and it's trying to get the wall into this position. That would take a lot of compression and pushing of that soil wedge. And if you pushed harder and harder, you can almost imagine it's like a bulldozer. As you push and push and push, at some point the soil is going to fail and it's going to shove upwards along some failure plane. And it's going to be pushing this whole wedge of soil. If you're at this arrow and you're a bulldozer and you're pushing, it's going to fail and it's going to bulge up over here. And it's a lot harder to do that. So your KPs, your passive coefficients, are typically much, much higher, an order of magnitude higher than these active coefficients. And so this is kind of just we're talking about lateral earth pressures. And so there's coefficients because we know that we can calculate the verticals. We've been doing good at that. We've been calculating that for a couple of weeks now. We know vertical stresses, and now what we're learning is, there's a horizontal component to that. but it's not just 1/2. That's a rule of thumb. There's actually a calculation. You can figure out exactly what the at-rest pressure is, the active lateral earth pressure, or the passive. You can calculate these, and there's 3 different ways to figure them out. And so that's what we're going to cover in today's class. Let's see. Any questions so far on what we're talking about? Man, we are running low on time today. So, but that's okay. We're gonna have 3 sessions to cover this. I do not plan on getting through everything today, but I really want you to kind of just understand what's going on here. And so this is in your book, and what if you could imagine you were a wall, and I think the video that I asked you to watch after this class has this exact same explanation, and explains so that you can understand the difference in passive and active and at rest, these coefficients. So, but just imagine if you had a wall and you're able to put a little sensor on this wall, and the wall was holding up some soil. Ignore that line. And this sensor, if you pushed on the wall in one direction, right now it's at rest. If you did nothing, it would be at rest. But if you started pushing on the wall, this would slowly start feeling the force, like it'd be the blade. Imagine this is the blade of your bulldozer and you're pushing it into the mountain. It would start feeling the stresses increase. And so it starts at rest right here. This is your sensor. And it starts at rest. There is some pressure, and it's feeling the weight of the depth of that soil times its unit weight. It's already feeling some type of horizontal lateral earth pressure. And that's what we call the at rest. But then as you're a bulldozer and you start pushing on that, it's going to keep going up and up and up. And that little scale is going to read increased pressure. And you're only reading the horizontal pressure. It's going to go up. But then at some point it flattens out. What would this flattened line mean? Why can't the pressures keep going up? Can't that soil just keep holding that bulldozer at unlimited and just keep going up and up? Why would it plateau like that? What do you think?
Maybe that's your point of failure.
Yeah, so what's happening at that point? Once it hits up here, what would that look like, Garrett?
Well, it should dive off eventually, right?
Yeah, I mean, so what's happening is your boulder is pushing and pushing and pushing, but then it's going to fail. There's going to be some wedge, and this whole mass is going to slide up, and it's going to bulge the ground up here. You're not going to push the whole mountain, across, but you're going to push, and then it's going to start sliding up on you. And so at that point, the soil can't resist anymore, and your KP, you have your maximum passive pressure, and it just keeps sliding along that plane. But that's a pretty big jump. I mean, the difference between your at-rest coefficient and your horizontal passive condition, that's a pretty large amount. But look at this tiny amount right here. This is, wow, so that would be similar. So here's your gauge right here. And as you started, let me erase this. So my drawings look funky because my mouse just draws these crazy lines sometimes. But the point is, if you've got your wall, and this is your ground level, and let's talk about the active case. And this wall is being like, someone tied a rope to it and they're pulling this wall. As you kind of pull that wall, all of a sudden the soil is not bound by anything. It free falls. It's like if you removed a dam of water, the water would rush out. Or if you move this wall away, the soil would lose its vertical strength. There would be less holding it in. And so that's what this side of the plot represents. As you start removing that wall, it loses horizontal stresses and it relaxes and it tries to slough down. And it relaxes and relaxes, but then it stops at a certain line. And where it plateaus, that's kind of the failure plane that we talked about, slope failures. And so that's why it doesn't go on for infinity. But as you can see, the magnitude of the difference as your coefficient, your horizontal coefficient, from at rest to active is really tiny compared to going from at rest to passive. So that's the whole point of this slide. And I've got 3 more pictures to kind of show the same thing. Anyway, I don't know why I wanted to show that picture, but these are kind of the things that are going on here. If you were this wall right here, and you were pushing this direction, no, that's not a good example either. I'm not going to talk about those pictures. I'll just confuse you. So let's calculate these. We can figure these. We can figure out what this horizontal stress is right here. And this is very similar, but just a little different than calculating vertical stress. So for the last few weeks, we've been figuring out vertical stress. Now we want to figure out, well, what's that horizontal? And so under dry conditions, let's just first talk about at rest. It can be calculated much the same way as vertical stresses. The first thing you have to do is you have to you pretty much have to figure out vertical and then convert them to horizontal. And so if you have a load, this is a load that's already like a surcharge load at the top of this wall right here. You'd have to figure out, okay, well, that load, you know, is applying some vertical stress down at this level, and it's also applying some stress in the horizontal direction. And so in order to figure that out, what is in the horizontal, you have to first kind of draw this stress diagram that takes into account the magnitude of your load. And so because it's a rectangle, that full magnitude of this surcharge acting in the horizontal direction pretty much can be summed up like the centroid of that mass that's acting on the wall happens at a height of 1/2. And so that surcharge weight is acting at this kind of the middle point right here, and it's acting in this direction. And then you have this triangle shaped wedge, and this is similar to calculating effective stresses. And as the deeper that you go, the more weight that you're feeling from that soil. And so this portion right here can be calculated similar to how we calculated our vertical stress right here. But when it's a triangle shape, we know that the component of the force from the soil acts at 2/3 from the top down. And so then you'd have to use statics to kind of sum the two forces and find the overall kind of the using the sum of the moments, figure out where, at what point the surcharge and the weight of the soil is pushing out against this wall right here. So to calculate some of these values, the vertical stress can be found by multiplying the unit weight by the height. So Z times the unit weight of your soil, and then you add in your surcharge. So that's what section number 1 is. Then the total horizontal stress can then be found by taking your coefficient. This is usually given to you, your coefficient of your at rest coefficient. That's what 0 is. If it's an A, it's active. It's a P, it's passive. And so you know that your horizontal, I'm getting an eraser here. Your horizontal component is equivalent to the at rest coefficient times the unit weight of your soil, the effective stress, the vertical effective stress. So that's how you change any vertical into a horizontal. You figure out, you have to use the coefficient, either the at rest, the passive, or the active, and then you can figure that out. However, if there's a water table, you also have to put in the pressure of your water. You can imagine if you were a wall on a swimming pool or something, that wall is that water in your swimming pool is pushing on that wall. So if you have a water table, you have to calculate how much water you have. And so you have to do the depth of the water times the unit weight of the water. And that's another force that's acting on your wall in the horizontal plane, which is a little bit different. Before we were able to ignore this, but now no longer can we. All right, so what are the equations to calculate the coefficient in the at-rest coefficient? It's pretty basic. It's 1 minus sine of the friction angle for normally consolidated soils. And if you have over-consolidated soils, the equation is just a little bit more complicated. You throw that in here and you can figure out what it is. So let's just talk about this for a minute. We've got 10 minutes of class. We're definitely not going to finish everything we had today, but just look at this first equation right here, just to understand the coefficient at rest. What's a typical friction angle of sand? Who knows that? The top of their head. Throw one out there.
30 degrees, is it?
Yeah, 30 degrees. That is a very standard average. And so if you did sine of 30, what does that equal? can do it on my calculator.
1/2, right?
Yeah. So 1/2. So the coefficient, the lateral coefficient of the at-rest earth pressure is 1 minus sine, let's say 30, which would be 1 minus 0.5. So you can see why, on average, it's acceptable to use an at-rest coefficient of 0.5, because 30 is a pretty common. Now, what happens if you increase your friction angle? What if you have better material? What if you have sand that's more angular and jagged and actually has a higher friction angle? That if you put in the direct shear machine and try to tear it, it would have a higher resistance to shear and therefore a higher friction angle. Let's just say, what if we had sine of 45? What's sine of 45?
√2/2.
Okay.
About
No
0.7.
one knows what that is.
0.71.
0.71. Okay, so what's 1 minus 0.71? It would be 0.3. So you can imagine that the coefficient goes down for the better the material that you have. And so it's saying that, let's just keep it simple. If your vertical forces were 100, and to figure out what your horizontal is, you just take your vertical and multiply it by K naught. Why does K naught go down to like 0.3 if your sand, your friction angle goes from 30 degrees to 45? Like, what's going on there? Why do you have less horizontal pressures in higher quality material? How do you explain that?
Is it because less would fail? So like you have less weight pushing on the retaining wall and more pushing on the soil?
I like where you're going with that. You've got the concept. So
Greater shear strength?
yes, and so shear strength means that the soil can hold up itself on its own better. It doesn't need a wall. So this is what a stockpile would look like with the sand with a 30-degree friction angle. But then this is what the stockpile would look like if the sand had a 45-degree friction angle. And so if you put a wall on this, it's holding up a lot more, not proportionally, but it's holding up a lot more than if you put up a wall on this. Triangles don't look proportional, but the sand is holding up with a higher friction angle. The sand can hold more of its own, and it doesn't need, and so there's less acting in the horizontal direction, if that makes sense. Any questions about that?
How would saturation of soil change K?
Ah, that's a great question. So the saturation of soil, so K is not figured out by saturation. It's only the at rest. The only thing that affects K is the friction angle of the sand. So K stays the same. However, what you're saying is, well, let's add a water table. Like, what if there was a water table, on this soil right here? What would that do? Well, that would add water pressure. So whatever depth that you had of water, it would be that times 62.4, and you'd add a whole nother triangle over here of water pressure. And we're going to get into that probably next week, but that's what saturation does. Your K stays the same, but water adds a significant load. So that's why when people design walls, they try to put weep holes. Has anyone heard of a weep hole before?
Yeah.
What's a weep hole?
Lets your water flow through the wall, but it holds the soil back.
Yeah, so and it's as simple as drilling like little holes in the face of your wall, so that if there is a water table, if it rains or you're watering your lawn or something like that, that water can, instead of building up a water table behind this wall, it can find a drain, like a bathtub drain. A weep hole essentially is just a drain for your wall. And sometimes they even put really coarse gravel about 3 feet behind these walls, especially when you design MSE walls. And we'll talk about that later. But you're required to put a high draining permeable material behind most walls, so that if you ever get water in there, it will drain out immediately and it won't add that huge hydrostatic pressure trying to push and topple your wall over. So good question. Let's see. Anyway, so to calculate your horizontal your at-rest lateral earth pressure, K naught, you simply can sum up all of your vertical forces that are acting on that wall, and then you can calculate your K naught by one of these two equations, and then you multiply your vertical by your horizontal, your vertical stress by your horizontal coefficient, and that equals your vertical. Or, well, I said that backwards, but I think you might know what I mean. Let's look at it again. I guess I'd kind of jumped the gun, but this is when you add a water table, essentially what you're doing is you're adding the unit weight of water to kind of all the pressures that are acting on this wall right here. And so the total pressure is the sum of all of these different shapes right here. This first point right here, this is all represented by your surcharge right here. This is the load, and it's a uniform load that's acting, and it creates a pressure that's kind of trying to push this wall out right here. And then you've got each of these other shapes to consider, but sometimes it's kind of hard to draw these shapes, and so you can simplify the shapes any way that you want. There's no like right way to do it. The key is to just draw as many as few rectangles and triangles as you need in order to calculate these values right here. And you're just trying to sum up all the different forces that are acting on your wall, trying to push it over. And that will help you calculate knowing the vertical stresses, you can then figure out your horizontal forces that are acting on your wall. And so you'll notice each of these vertical pressures is multiplied by a coefficient, and we'll see that depending on what condition you're in, you're going to either multiply these rectangles and triangle pressure, these influences, by either the active, the passive, or the at rest. And so that's kind of what we're dealing with right here. So the last 2 minutes, could you find the lateral earth force at rest per length of wall? And could you also find the location of that resultant? Because the soil is probably going to be in different triangle shapes, but how would you go about doing this one? What's kind of the strategy? We won't do it here, but does someone want to just kind of blurt out kind of the strategy to figure out what your lateral earth force or pressure is?
You find our K naught first.
Yep. And what equation would you use to find K naught?
1 minus sine of phi.
Right. And so here we're given phi is 30 degrees. Oh, here it's 30 degrees. Okay, so we know K naught. That's part of the equation. Then how do we figure out all these effective stresses that are going to be acting, horizontally on our wall?
It's K naught multiplied by the unit weight times the depth.
Mm-hmm. So if this was all sand and there was no water table, then the sand would probably create some type of stress distribution that looks like that. For every foot that you go down, you're multiplying it by the unit weight. And so if it was 10 feet down and the sand weighed 120 pounds per cubic foot, down here it'd be 1,200 pounds of pressure overall. And then we would know that pressure would be acting at 2/3 from the top or 1/3 from the bottom, and that would kind of be the resultant force of that. And then we'd multiply that by K naught, and that would give us our total lateral earth pressures that are acting on the wall. So I know we had about 1 second to cover that, but that's okay. We're going to have 2 more class sections. We'll start over here on the next one, and we'll keep diving into this. But essentially, they're all the same. You need to figure out the distribution of the pressures. And in this case, we had the pressure from this first layer, and then we add the pressure, the increase. There's water in this one, and so you can see the unit weight goes up, and so that's why this is a little bit more. And then we add the pore pressures from the water, and adding all those together, and then figuring out that each of them has its own resultant, and it's just the sum of the forces. The sum of the moments equals 0, and we can figure out at what depth z that we're acting on. Anyway, that's lateral earth pressure in a nutshell. This is kind of the solution I just want to throw on here, but I'm going to stop right here. But the forces that man felt when that trench collapsed can be calculated using these equations right here, and they're powerful, and It's why walls fall over. It's whenever you see an old retaining wall that's been in place for a while, usually the top's starting to tilt and lean over. The earth exerts a lot of lateral pressure. We've been mostly focused on that vertical pressure to figure out bearing capacity, but bearing capacity has this horizontal component that we'll start exploring over these next two classes. So we'll stop right here for today. Any questions? Any questions about the test that's coming up? So I'll put some announcements explaining some of the things I talked about today, but you can sign in this Friday, 15 minutes early, probably 20 minutes early just to be ready. But I'll make the quiz available in Canvas that you can start taking. I'll watch you all on Zoom just like this. You'll have 90 minutes to take the test, 15 minutes before class starts to 15 minutes after class ends. 90 minutes to take the quiz, or the first test. Any questions? All right, good luck. You guys will do well. I'll see you on Friday a little bit early, and just email me if you have any questions, and we'll go from there.